Charles and Florian, for inviting me and having me here. We're happy to be in by data. I'm located in Israel. Right down the time at my place is 3 a.m. So if I doze off, please make sure to wake me up. With me, we have also Netzer, which is our CEO of DataHeroes. I myself, my name is Eitan Netzer. I'm the chief scientist of DataHeroes. We share a last name because Oren happens to be my brother. And I would like to start my presentation now. Just 1 second. Can you see my screen? I cannot see you guys. So
yes.
wait. Okay.
Oh,
so,
if you want, you can do picture in picture, and then you can see us. If it helps.
No, that's fine. Now, I will stop at some places for questions. Okay, so I won't go too fast into it, but I'll stop at strategic places for questions. So we are DataHeroes. We have built a Python-based framework and data structure for data-centric AI, and we'll go into that in a bit. So first, a bit about myself. I've done my BEC at computer engineering at the Technion, done my master thesis on brain signal analysis for training AI models. I've been a data scientist for roughly 12 years. And before studying DataHeroes, I started my PhD on a topic that is called Coreset, that we'll go into in a minute. And after some time studying it as a PhD student, I decided I want to stop my academic studies and turn it into an actual product, and joined forces with my brother and Liran Sigalat, which is our CTO. And let's go into Coreset a bit. So the way that I see it, there are 3 big challenges in machine learning, especially when using big data for training. The first problem, and probably the biggest problem and issue making a good model into production, is having a high data quality and controlling it, especially when you're talking about big data, and it's probably the #1 reason for failure. The second problem is, as you work and train your models, it can take between hours and days to train a model, and you repeat that process time after time. Even during cleaning your data, you clean your data, train your model, and evaluate to know where you are. That can be done dozens or hundreds of times. As you train and you do hyperparameter search, you can repeat the same action hundreds of thousands of times. And even once you're successful and already gone into production, you have to keep your model fresh and update and train with new data coming in. Otherwise, your models can become stale and you'll be very affected by the drift. So all of those problems share a common problem of the time that it takes to train a model, and we're able to solve all of them using something called a Coreset. So what is a Coreset? A Coreset is a small subset of the entire data that will preserve the statistical properties with respect to a given cost function or model or an algorithm. If you take a look on the illustration on the right, you can see on the top that we have a lot of data points. And as a data scientist, to work with the entire data could be very frustrating. Every experiment that you're running can take a long time to train. If you want to get into your data and actually know it very well, it's hard to do that. And what we are providing using a Coreset is coming from big data to small good data. What we are able to do is select a very small subset of the entire data, assigning a corresponding weight to each data instance in a way that preserves both the statistical properties and edge cases of the original data. So it's important to keep in mind that a Coreset is a weighted subset, and you need, in order to compute it, you need two things. You need the features or the feature layer embedding that you're depending on, and the desired cost function that you want to use. There is a different Coreset for every cost function. Those two are very important in order to compute a well Coreset. And in general, the way to compute a Coreset is you start with your data set and the desired cost function. For each instance, you compute a property that is called importance. In some papers, it's called sensitivity. You can think of importance of how important that data instance was to the model and how would it affect the model with it or without it, how much it was affecting the model. Once you have this importance property for each one of your data instances, you can construct a corresponding probability space using that importance, select a very small sample out of your data that keeps statistical properties and edge cases, assign the corresponding weight, and then you can train on that small subset with weights the same model to compute, and you'll get the same results with the fraction of the data instead of the entire data set. Is that making sense? I'll stop here for questions.
Makes sense.
Great. Okay, so with that in mind, let's see a little bit of a
Oh, we got one question.
Sure.
I'm in hot. 1 sec.
Can somebody
I'm up here.
in the office itself? Okay, yeah.
Okay. This might be basic, but is the importance just another word for a weight? So are we like taking the weight of a weight?
No, it's not exactly. They are a function of each other. Okay, they are related to each other, but it's not exactly the same weight. The importance is a bit different. It's how important it was for that instance was for the model, and the weight is after you selected the subset, you assign the weight in order to preserve the original cost function. They are very related to each other. There are almost an inverse, but only for the samples that were selected. So very related to each other, but they're not exactly the same.
Okay, cool. Thank you.
Sure. Okay. So with that in mind, let's look a little bit of a benchmark. We've taken a data set, the poker hand data set, which is roughly 600,000 instances. And we computed the area under curve on a hidden test set. You can see the area under curve over here for the full data set. Now, when we take a random sampling of the entire of the data set, taking just 1%, you can see that the area under curve is really affected by it, and it's much lower. We had to go up until 15% of the data to get an area under curve that was close to the original 100% of the data. Now, using DataHeroes Coreset, we were able to use just 1% of the data and get the exact same area under curve as if we were using the entire data set. Okay, so having this algorithm of a Coreset to select a subset, we utilize in DataHeroes in order to build a very efficient and fast data structure that you can manage your data and models, and we'll go into that. So you can take our Python library and call the build function. Given the data that you're giving it your data, it will take your data, split it into batches. In this case, x1 till x6, x7 until x12, and so on. And it will compute a Coreset for each one of those batches. Now, Coreset has a very unique property when you can take two Coresets, union them together, and build a Coreset over that. So after we got C1, C2, C4, and C5, we're building the next layer, C3 and C6 in this case, that is combining both of the nodes under it. Okay, and of course we can keep doing that until we get to C7, which is the root in this case. And now each node represents all the data points below it. If you take a look at C3, it will represent in a Coreset the data between X1 and X12, and C7 will represent the entire data set under it. Now we can take our fit function and compute a Coreset over each one of those, and compute the model over each one of those Coresets. Okay, so if you compute your model on C7 using the fit function, you will have a model that represents the entire data set. The same goes if you decide to compute on C3, it will build a model on all the data below it. Now we had a function, as we were building, we had the opportunity to make the partitioning of the data with some business logic. It's not a must, but it's a possibility. For example, the simplest example would be a time series that you can partition your data using some time series, and then if you are looking on the entire year, it's at C7, at C3, you could imagine that you're just looking at the first half of the year, and so on. Now we have that fit function as part of our library. There is also an API call just to get the indexes of the data and the weights if you want to keep your original stack and work with your original stack without changing your scikit-learn or PyTorch or whatever library that you're using nowadays. Now you're probably noticing that there are some data missing over here. And that's because when we're getting new data, X22, X23, and X24, in order to update our model, we don't have to throw all of our computation and compute the model from scratch again. All we need to do is update C5, C6, and C7 with a fraction of the computation. And now when you want to compute your model on C7, it will be updated with the new data with ease. And we don't have to follow all of the computation that already done. So doing that is very easy, very fast. Everything is managed by our library. Now, the same logic goes if you decided that to go into your data and you discovered, for example, that X17 was either a noisy label or some other problem, and you want to remove it or change the label of that data instance. All you need to do is use their API calls to tell X17 either remove yourself or change the label. All we need to do is update the relevant path, C4, C6, and C7, and we have an updated data that we can rerun the model on it in a fraction of the time. Okay, is that making any sense? I'll stop here again.
Yeah, Eitan, I think you have some questions in the chat.
Sorry, can somebody read them out?
Yeah, there's a question: what edge cases exist where this methodology struggles or fails?
I have to say, if the number of instances is very low, especially if it's lower, close to the number of features. If it's close to the number of features, then it could be we can have a problem, because all of the computation and all of the complexity is and the sampling is based on the VC dimension and number of features. So if you don't have a large data, it will not be as good if you have less features than instances. But we will see another use case where you can still use that, even though we don't have a lot of features. Other than that specific problem, there's no incentive not to use this technique.
Eitan, I have a question. I already know the answer, but it's important to ask it so people understand down the road what's going to happen. What happens if I change a model? Do I have to reconstruct the tree?
Yeah, as I said, the Coreset is per cost function. So if you are using a logistic regression or using a k-means or using linear regression, it's a different core set. You have to start from, you have to give that as the initial information. If you're studying now, you want to do something new, then you have to do it from scratch.
Thank you. This is important so people understand.
Thank you. Anything else on the chat? Great. Okay, so let's look at a little bit of a benchmark to see where it helps. We've taken a data set, and we started with data set had 20 million instances and 10 features, and we were computing a logistic regression model. We started with 2 million data samples and added more data to the model and trained it. In the traditional way, when you keep training on the full data set every time from scratch, as you see in the red one, the compute time started at half an hour. As we growed and added more and more data to the model and got up to 14 million data instances, it took 2 hours to train the model. While on the contrary, when we're building the Coreset tree, the initial build of the 2 million samples took 17 seconds, and then updating and training on the new data and on the updated Coreset tree took between 5 and 10 seconds at each iteration. So that you can see in blue, they're not even close to each other, the blue and the red one. So coming from half an hour to 2 hours, we're able to cut it down from roughly 30 seconds at most using the Coreset tree. So what we imagine is that you can take your existing stack and the way you work, and if nowadays every operation can be very slow and takes the time because of the training time, okay, that after you prepare your data, you clean it, build a model, evaluate, and keep going like that until you get to the hyperparameter search and model updates. With our DataHeroes, each step can take a very long time. The cleaning part can take weeks or months. Because of this bottleneck, the hyperparameter search can take a few weeks because of that. And you choose not to update your model very frequently because of the cost, both in resources of time and compute. Now, with DataHeroes, you can take your existing stack and speed all of your operations because of this almost real-time interactive mode that you can do everything a lot faster.
You had a question in the chat. I'll interrupt you. The question was if your data set is biased after computing the Coreset, will it stay biased or will it improve it?
No, it will stay biased. In order to keep the good properties of machine learning and to approximate the same one, we have to keep all of them. We cannot choose just to get the good stuff out of machine learning. So if the data is biased, doing a Coreset over that, it will stay biased. We're not solving those problems, but it will be easier for you to interact with your data and play with the different weights and try to get a different weighting and play with it, because each experiment that you'll do now will be blazing fast compared to the old methods. Okay, so I want to take the time to show a few use cases of how you can use our library. The first one is data cleaning and anomaly detection. I hope that you guys remember the importance property that we were talking about. Now, there is a very interesting phenomenon with those importance. As I said, the importance is a way to measure how much each data instance is affecting your model. You can imagine a procedure of leave one out that will tell you how much each data instance is affecting your model because you're doing a leave one out. Of course, we're not actually doing a leave one out because that will be very slow. We're doing some other things, but you can imagine a leave one out procedure as a way to imagine what is being done in the background, but in a faster way. So we've taken some data, and if we compute the importance of the clean data points and the noisy data points, and show both of them on compute and histogram for both of them, you can see that in the blue one, and the importance in the x-axis is the importance. You can see that the behavior of the importance is pretty low. It's much lower, while the importance behavior of the noisy data is usually a lot higher. Okay, as you can see over here in the histogram. So we can use this property in order to clean our data set, because it will give us a measure of which data instances might have a problem with, and we should check it out. So we've taken ImageNet and computed the importance for the data instances over there. And one of the classes is actually called missiles. And on the top row, you can see examples that got a low importance, meaning that they were fitting well with our model. As you can see, there's no doubt all of those examples are missiles. There's no doubt about it. On the contrary, you can see on the lower row, on the bottom row, a few examples that got high importance. Now, it's very important to emphasize, this is not the answer of the machine learning model. This is the annotation given by ImageNet that's supposed to be human annotated and verified. And those examples got a high importance. It's simple to see that none of them are actual missiles. Those are pencils, those are umbrellas, and this one is actually a rocket and an amusing part. So all of those examples are not actually missiles, and the importance property, we're able to distinguish them out and see that there's a big difference between the one that makes sense and the one that are not making sense.
Hey, you just have some questions in the chat.
Yeah.
The questions are, has this methodology for training Coresets been published somewhere?
Yes. Coreset research has been studied in academia for roughly 20 years. It's originated from computational geometry. The community of Coresets is very small. It's getting larger in latest years, but it's been published. I have to say, we'll see in the end. But in our website, there is a section for the more academic part and explaining about the research. Being an early research topic, it's not organized yet. There's no introduction to Coreset book or anything.
There is a wiki page someone just posted.
Sorry?
Someone just posted the wiki page, so thanks for that.
Great.
There's another question though.
If I could just add to what Eitan said, in Coresets, and Eitan, correct me if I'm wrong, but there is it's actually all it's not empirical. There's actually proof of everything here, right? It's not empirical. There's actually proofs in each one of the papers.
Yeah, thank you, Ron, for that. Yeah, part of the reason why I started to learn that as a part of my PhD, I was very fascinated by the fact that all the research is not only empirical, it's also theoretical. So for every Coreset, for every paper, there's a proof about everything. This is part of the reason why you need the courses for every algorithm or cost function, because you need to prove that with respect to the relative cost function you're trying to solve. So yeah, thank you, Oren, for that. Yeah, everything is proved with mathematical guarantees in everything.
And then there's one more question in the chat. So that is, will this importance score work for any type of ML model? For example, for more complex models such as neural nets, it might be more difficult to assess the impact of an individual data point.
Okay, in terms of deep learning, in order to do that, we're not taking the entire model in order to compute the importance. What we're taking the last feature layer to use as embedding. And once you have that last feature trained for embedding, you can use that in order to do this importance computation.
You got a thumbs up. Sounds good.
Great. Okay. So
There was another question, Eitan, on how customizable is this importance calculation?
I'm not sure I'm getting the question. What do you mean customized?
Eric, do you want to clarify?
Eric?
In the chat, he says, can we change the calculation for importance at all?
The calculation for importance is related exactly with the cost function you're trying to compute or to minimize. So if you have a different cost function, it will change the importance. You cannot just change the importance because it's a fundamental property of the cost function you're trying to create a Coreset for. So you cannot change that. It will not make any sense.
He says if I have multiple criteria or cost functions.
Okay. The theoretical answer is that you can add those importance for each measure, for each metric that you're using, and then you'll have something that is combining all of them. Right now, doing that with the library is not simple, but it's something that could be supported in the future, that you'll add up different importance from different cost functions and support a variety of cost functions. At the moment, you'll have to compute each one on its own and work on each one on its own. Any other questions? Okay, great. So we've taken the CFAR data set and added noise to that, meaning that we've taken some of the labels and may change it from the correct label to a wrong label. Now, we were working in iteration, looking at roughly 20 images at each iteration, and comparing a few methods of cleaning and getting how to identify or alert about possible noisy labels. Okay, so we have in red randomly trying to look for data points that are noisy and have a wrong label. As you can see, using that to find anomalies in your data and fixing those samples is very slow. On the x-axis, you have the number of seen images, and the y-axis, you have the amount of fixed samples. So using that in a random manner is very hard. In yellow, what is called CF is a method called confidence learning. I will not go into deep about that. But in a brief, imagine doing a cross-validation to your data set, and every time there's a difference between the prediction of your model and its and the correct label of on the corresponding fold, it will mark it as a mistake and an anomaly. Okay, so you can see that is a much better, more effective way to find the problems in your data and correcting your labels, much more effective than random. When you take the DataHeroes approach using the importance in blue, you can see that we're computing those samples a lot faster, and we're finding at each iteration more and more samples that need to be fixed. Okay, so this is when we're looking on the number of fixed samples at each iteration. This is actually what will happen in measure of area under curve. In the green one, you can see the original data without adding noise, what would have been the area under curve. And the y-axis is the relevant area under curve that is computed. So you can see the same colors as before. The DataHeroes area under curve at each iteration is growing much faster. Okay, getting much closer to the original clean area under curve on the top with the green. Okay, the random one is pretty much in space, stays in the same place, and the yellow confidence learning is growing a little bit, but not as fast as the DataHeroes using the importance approach. Now notice something very interesting. At each iteration, we're recomputing everything, or recomputing the method to find those anomalies, or we're evaluating the model, or we are training the model. Everything at iteration. Working in iterations is very problematic for confidence learning, because in each iteration you have to do cross-validation on your entire data set. So you can see over here that on the y-axis, the compute time of the confidence learning approach is very slow. It can take you more than 5 minutes per iteration. Now, because of that, you have to do it with a lot of samples iteration. It's very hard for you to evaluate each time. You don't want to make a lot of iteration. While with the Coreset, it's very fast. And if you take a look comparing the Coreset versus the random, you can see the difference between them is very slow, meaning that the time for computing the model and doing valuation is most of the time. It's most of the time is used to compute those, not to compute the importance. So each iteration, we are recomputing both the Coreset, which is computing the importance, computing the evaluation, and computing the model. Okay, so all of those iterations, all of the cleaning work as promised is not only more effective, is actually being done faster. Are there any questions before I continue? Great. So let's look on our last use case. We already looked on a very similar plot earlier. Okay, this is similar data that we have data growing as you add more data to your original model. Sorry, the training time using the traditional method is getting very slow. You can see on the y-axis the time to train, and on the x-axis the number of samples. So doing that in the traditional way in red, adding more data and computing a model on the entire data set that you have is very slow and growing linearly. On the contrary, the blue line, that each time we're adding more data to the Coreset tree, it looks as if it's constant. It's not exactly true. It's only because of the scale. It's actually growing logarithmically, but it's very hard to tell. So adding more data is still, even though you added more data, it's still easy to compute a model, and it's very fast. Now, this data set had a drift in it. Now, because we were able to train a more updated version of the model a lot easier, because we don't need to compute a lot of time, we were able to have a lot more training done in a higher frequency than the traditional method. If you look at this graph, the x-axis is the number of samples being added, and the y-axis is the accuracy of the model. You can see both of the red and the blue are starting at the same accuracy. And after a while, roughly around the after 6 million samples, there is a drift in the data. Now, because the red is being updated in a low frequency, is very affected by the drift. It's really affecting it, and it's hurting it because the model is not updated. On the contrary, the blue line using the DataHeroes Coreset is being updated in a very high frequency, so it's not being affected by the drift as much. As you can see that after time grows, the difference between the Coreset tree and the full traditional method, the difference between them becomes very large and too big to handle and too large to handle. Is that making sense?
Good.
Great. Okay, so notice there is no difference. The way that we compute, we're getting the same properties of the model as we compute a Coreset. We're getting the same model. It's not magically unaffected by the drift, but the fact that we can train it in a higher frequency helps us to avoid those effects of the drifts. Now, we see this approach as a fundamental shift in the way that you develop and maintain your models. Okay, starting with your original data set, you actually create a Coreset out of it, and then everything can be done in the Coreset and now on the full data set. If that's exploring your data, cleaning it, labeling it, training it, doing hyperparameter tuning, and in production, getting a feedback and keep doing the same things, now everything becomes a lot easier. Instead of working with your heavy lifting original data set that can be terabytes of data, now you can use with a very small subset of the data, making everything not only fast, but also easy without having too much overhead in every operation that you do. Now, we are happy to share our vision with Professor Andrew Ying, that is a very strong believer in Coresets, being very helpful to push on the data-centric approach and to improve the way that people develop and maintain models. He's a very big believer in. He's the one of the originated of the data-centric approach, and is a very strong believer in Coresets and doing so. You can take a look in our website, DataHeroes.ai. We have resources. We have both introduction to Coreset that has a lot more information of the academic side of it. We have documentation and tutorials on a variety of things, and we'll keep adding more tutorials. And what you need to do is just to try a library is just to create an account, do a pip install, and then you can try out our library and see it working for you. Right now, we have support for logistic regression. In a matter of weeks, we'll have support for PCA, linear regression, and k-means. And decision trees will be supported in 2 months. Now, notice that even if you're doing deep learning, you can use us for cleaning your data or update your model in production, because you can keep the layer frozen and just use the last layer as a feature extraction, and then you can use it both for cleaning and model maintenance.
Just to clarify, the cleaning use case that Eitan showed before is available. Basically, it doesn't matter what model you're using. In terms of the training examples that you've seen, like Eitan said, logistic regression is already available, and the others are coming very soon. And the other thing is this, we didn't mention it, the library is completely free, and we'd love for you to give it a try.
Yeah, thank you for that clarification. Okay, you have both of my emails and Oren emails here on the bottom if you want to interact with us. And as Oren said, our library is completely free. We'll be happy that you give it a try. Any questions?
I have a silly question. It's not about this, but do you have a Conda install as well?
Sorry, come again?
Conda install, not just people. I'm asking because the next person after you is on a Conda and they basically do Conda, so it's easy for to ask them.
No, we don't have a Conda yet.
Okay, it's pretty easy to do. We can talk later on how to do it.
Okay.
Yeah. Thank you. Thank you again for having us. Really appreciate it.
I have
Really enjoyed it.
Just a second.
Well,
Thank you.
Sorry.
Thank you for having us. I want to take Pi Data, Jacob.
Thank you very much for coming and presenting.
Thank you. I want to thank everybody that invited me. It was a pleasure to be here, and be happy to be here again. I'll be even more happy to be in person, not to be on a different continent.
It'll be a little warmer. It looks like it's snowing there.
Yeah.
Yeah, not exactly.
Virtually slowing. Eitan, when
It's
you,
80 degrees, I think.
I don't speak Fahrenheit. I cannot confirm or deny. I use the metric.
it's 60 something, 67 something like this. When you come to Austin or near or to Texas, then make contact. We'll arrange for you to present whatever updates you have.
I'll be happy to. So thank you very much. It was a pleasure.
Appreciate it.
Cool. You want to take like a little break or now? Should we just move to the next speaker?
A little break is always a good time.
Yeah, we can stretch our legs
Yeah,
here.
Do a little break in the room.
We can take like a 6-minute break and come back at 8. Sounds great.